Good morning and welcome back to Vandenberg Air Force Base in California for today's second briefing. This one will focus on the 5 NASA-sponsored CubeSats that will launch into space aboard the United Launch Alliance Atlas V rocket tomorrow morning. Liftoff is scheduled to occur at 5:49 a.m. Pacific time. And to discuss their CubeSats, we're pleased today to be joined by Richard Welly, Director of the Microsatellite Systems Department at the Aerospace Corporation and Program Manager for OCSD. By Tim Olson of Salish Kootenai College in Pablo, Montana, and the PI for BisonSat, the first CubeSat from a Native American tribal college. Morgan Johnson from the University of Alaska Fairbanks, team lead for the ARC CubeSat, the first CubeSat from the state of Alaska. Jerry Buxton of the Radio Amateur Satellite Corporation in Silver Spring, Maryland, and the PI for AMSAT Fox 1. And Courtney Duncan of NASA's Jet Propulsion Laboratory in Pasadena, California, and the PI for LMRST SAT, or LMRST. Thank you all for joining us. If you're watching today on TV or through the web, after we have opening remarks, we'll be happy to take your questions from social media during the Q&A portion. To get your question in the queue, please use the hashtag AskNASA. And for media who have dialed in on the telephone, please remember to press *1 to be placed into the question queue. And we'll start off with a few opening remarks from Rich.
Good morning. My name is Rich Welly. I'm with the Aerospace Corporation. For the past 10 years or so, I've had the privilege of being the director of what is now called the Microsatellite Systems Department at Aerospace. Members of this group pioneered kilogram-class spacecraft back in the mid-90s and flew their first satellite, a pair of 250-gram satellites in 1999. Since then, the group has developed and flown more than 25 satellites in this class, with the maximum being up to about 5 kilograms. In keeping with the charter of the Aerospace Corporation, these have all been tech demonstration missions. 12 of these have been CubeSats, and of those 12 CubeSats, 8 of them are still operational in space. In addition to my role as director of this department, I am the program manager for the Optical Communication and Sensor Demonstration Mission. This is the satellite that Aerospace is launching tomorrow. This is a 1.5 unit CubeSat. It's our most ambitious satellite project to date. We've been developing this one for about 3 years. It's a 1.5 unit satellite. Its primary mission is to demonstrate optical communications in a CubeSat. This has been an interesting challenge for us. Our goal with this satellite is to achieve communication from LEO to ground at data rates that are a factor of 100 higher than what has been achieved so far in CubeSats using radio frequency communication. This is achieved in this satellite by developing a compact laser system and a precision attitude control system to point the laser at the ground station. This compact system will add significant capability for not only this CubeSat but other CubeSats, and it's expected that this could also find utility in larger spacecraft as we move forward. The data rates in this system are high enough not only to support existing satellite missions, but so high that they can potentially enable entirely new classes of missions in CubeSats. In addition, optical communication has the benefit of reducing demand on limited radio frequency bandwidth available for LEO to ground communication. One unique aspect of CubeSats that we're taking advantage of in this mission is they're extremely low cost and to both build and launch. And because of that, we're able actually to fly an engineering model of this satellite. Normally when you develop satellites, you make an engineering model, you test it thoroughly in the lab, and then you leave it there, you build the flight models and fly those. But there are things you want to learn about satellites that can't be learned by testing them in the lab. So in this case, we're actually flying the engineering model of this satellite. This provides risk reduction and allows faster technology development. 6 months from now, we'll fly the 2 flight unit models of this satellite, and the final design of those 2 satellites will be informed by lessons that we learn in the process of flying this satellite. That pair will also have a second mission, a demonstration mission in that they will do proximity operations. They'll have sensors and propulsion systems to fly in close formation with one another, and we'll learn lessons about how to do that with these satellites. So I want to close my opening comments by expressing appreciation to NASA for their support for this, for the development of this mission. It's been a very interesting experience for us, and I think a very valuable one. I also want to express my appreciation to the NRO for the access to space. And finally, I want to express my personal appreciation to the team of more than 50 highly talented scientists and engineers at Aerospace who have contributed to the development not only of this satellite, but of the whole series of satellites that Aerospace has flown over the past 15 years. With that, I'll turn it over.
Thank you. So I'm Tim Olson. I'm chairman of the Division of Sciences at Salish Kootenai College and principal investigator for the BisonSat CubeSat that will be launched tomorrow as part of the Alana 12 mission. I'd like to start just by saying a little bit about Salish Kootenai College. SKC is a four-year college chartered by the Confederated Salish and Kootenai Tribes of the Flathead Indian Reservation in western Montana. We offer a variety of science and engineering and technology degree programs on our campus, and the Alana program for us has provided an opportunity for our students to be involved in the development of a spaceflight mission from the conceptual stage through multiple years of design and building the spacecraft, testing it, and preparing it for tomorrow's launch. And really our mission is primarily an educational mission. Our interest in participating in the Alana 12 program has primarily been to interest our students in considering a career in the aerospace industry in the U.S., either as an engineer or as a scientist, and to help address that national need of resupplying our workforce with talented people to keep the U.S. as a leader in this area. If you could go to my first slide, please. So our spacecraft is a 1U CubeSat. So this image here shows not the complete spacecraft, but in one of the preliminary stages of verifying that we could get everything to fit within the structure. Actually, pretty complicated technical issue on these small satellites to get everything to fit in the volume that we have available. So you see some of the components, you see the structure, you see some of the circuit boards that makes up the flight unit for our satellite. Our team has been, over about the 4 years of development, about 19 students, 16 from Salish Kootenai College and 3 students also from other tribal colleges, some in Montana, 1 student from the Southwest. And we've had 4 faculty mentors that have worked with our students. So that may sound like a fairly large team, but it really isn't. Students, they enter the program and they graduate and transfer on. So at any one time we would have 7 or 8 students that are doing significant work on the program. So being a small team, we had to make some very conscious design decisions about what components we would purchase. There is quite an industry out there now of commercial providers, both in the US and internationally, where you can buy components of CubeSats. So our satellite is a mix of those type of components, and then also components where we chose to take on the design and build those components ourselves to give the students the experience of that process. So in our case, those components that we've designed ourselves is the primary payload, a visible light camera, and 2 of the 6 solar panels, the antennas and the antenna deployment system, and then also our attitude control system that controls the pointing of our satellite for targeting the images we want to target. And just to finish, I'll say a little bit about what our science mission is. We're flying a visible light camera that consists of a image detector that's very similar to what you find in cell phones and in consumer grade cameras. It uses what's called a bare pattern filter detector, and that's an image detector where each of the pixels has a filter over the top, a little tiny filter over the top of the pixel, either red, green, or blue. And the way that you construct a color image from such a detector is by analyzing the brightness that the pixels have in those 3 different colors. And one of the science studies that we'll attempt to do with BisonSat is to use that bare pattern filter detector to do broadband spectroscopy to classify the land cover that we're seeing in the imagery, potentially also do change detection if the satellite is long-lived. And we're particularly interested in getting imagery of the Flathead Reservation and some of the other tribal lands around the country. A number of tribal governments are active in using space-based imagery for their land management decisions, and that includes the Confederated Salish and Kootenai tribes. And we hope our mission is able to contribute to the data set that those tribal organizations use. And with that, I'll pass that off to Morgan.
Awesome. Thank you. Thank you for having me here. My name is Morgan Johnson. I am a graduate student at University of Alaska Fairbanks. Our project is sponsored by Alaska Space Grant through our Space Systems Engineering Lab. Our project started off as a graduate class to teach space system engineering, and it's been 5 years since the class was started, and from there the project has definitely grown from the conception stages. Through the 5 years, we've had 36 students actually work on our project, from undergraduate, graduates, and even some high school students. With all of the research that's been done with our students, we've been able to have 4 thesis papers written for graduate students and have had 4 IEEE aerospace papers contributing to our satellite and other conceptions that we've been thinking about in our lab. So our satellite was designed to we have 4 mission objectives. And one of the first ones is our main science mission objective, which is to measure the thermal environment inside the launch vehicle. Now, CubeSats are placed near the engines in these launch vehicles, and so this environment's not well known for the satellites, and so we're hoping to measure this environment and provide relevant data to NASA and to other CubeSats so that they can better understand what this environment is that they're building their satellites for. 2 of our other missions are technology readiness missions, so that way we can build the technology for our satellites at our university. The first one is a attitude control determination system, to where we are focusing on low power, so that way, because CubeSats are really small form factors, there's limited power, and so we're using newer technologies to make that happen. And then additionally, we're working on, we have our comm system, which is going to take pictures of Alaska and be able to send those down to our ground station. Our last mission objective is our educational mission objective, where our focus is getting students to get hands-on experience working on these satellites. And working on that, we have, to start that program in our space system engineering program, we've started the students off building their systems on these our dev boards, and they start designing their system using these, where they pick what their science mission is, they develop all their electronics and interface with our microcontroller that we've chosen for our satellite, and they can prototype their system, and then they can take it to the next stage and build their actual systems. And so here we have a engineering model of our satellite, and you can see we have all of our different circuit boards, the solar panel boards on the external faces, and each of these boards were designed in software at our university, and they've taken it from the design stage to testing it to the final integration of our satellite. Some other things to point out: we just use really cheap off-the-shelf parts for our antenna. You can see we have a tape measure. It works for a UHF connection. We're using, for the launch environment data logger, we have to have our separate power system, so we're just using AAA batteries, which I don't know if you can see here. So we're just using AAA batteries. We're using a webcam for our camera, and we're also using the radios that we learned to use in our in our wireless sensor network class. We're using those radios to make our satellite work. So it's just really interesting to take this project from what we're learning in school and being able to produce a satellite that we get to launch and have it in space. So with that, I'd like to also thank our sponsors that have been supporting our project. So Alaska Aerospace has been supporting us for the last 5 years we've been working on this, and NOAA, which hosts our ground station, which our students also designed and built. So with that, I'd like to hand it off to Jerry.
Thank you, Morgan. AMSAT is officially known as the Radio Amateur Satellite Corporation, and we are a nonprofit 501c3 educational organization. which is comprised of volunteer amateur radio or ham operators. AMSAT has successfully been building, launching, and operating amateur radio satellites since 1969, and in 2009 the Fox 1 project was born and approved by the board. Fox 1 is our first CubeSat, and the design of it was to be able to include amateur radio and fly experiments for educational institutions. AMSAT works to involve the elementary through college students with easy access to our satellites and the data we can relay to the ground. If you would put the first slide, please. On the left-hand side, you see the CubeSat itself. The more significant picture in this case is the little girl holding the antenna. We design our radios to work with simple equipment like a light handheld antenna and the two walkie-talkies that you see hanging off her belt, so that you can provide communications. You can actually work with other amateur radio operators throughout the United States or around the world. Amateur radio operators can talk to each other through the satellite. And then we provide ground software as well. We give free ground software that's capable of receiving the telemetry that is sent by the satellite. The telemetry contains both satellite and the science telemetry. Anyone can use that to receive the telemetry and decode it and see what's going on with the experiment. So even if you're not flying an experiment, you can have access to the science in the classroom. And we also provide assistance with curriculum and classroom planning so that students can become involved with learning about the satellites, actually receiving it live, and working with the science that is brought down. All of the science that's collected through the ground station with the consent of the operator who's collecting it is sent to a central server where it can be accessed by anyone, and we will keep it there for a long time in order for anyone to be able to access and do studies of the various aspects of the satellite telemetry and also the science that's involved. As a nonprofit corporation, we're extremely happy that the NRO and NASA through the Alana program have given us the opportunity for this flight. It's a substantial contribution to gaining access to the science and education in space. The relative cost of developing the CubeSat for us is much less than the cost of the launch because we're all volunteer, and we spend a lot of hours in our own homes and working on these things. So the price of the CubeSat is really more that of components than anything else. The opportunity to fly on this mission or any future possible mission is a great promise to what we can see as an affordable way to reach out to students and interest them in space and space radio communications. If you go to the next slide, please. The Fox 1 was designed to carry experiments from other educational institutions. We've worked with universities to provide experiments to fly on the satellite. Our purpose was, as you can see in the diagram, that we've got 40% of the volume, the upper half more or less, in the multicolored boards that's devoted to carrying hosted experiments. We provide the power, we provide the radio link for the telemetry, and bring down the information from the experiments. For the experiments we're flying on Fox 1, we worked with Penn State Erie on a capstone project where seniors designed and prototyped an experiment that uses MEMS gyros. MEMS stands for Micro Electromechanical Systems, and they're going to measure the spin of the satellite around its axis as well as any precession or wobble around that spin axis. Fox 1 is stabilized with a passive magnet, which you can see on the left side of the satellite in that picture, that maintains the top or plus Z pointing end more or less pointing toward the north magnetic pole as it orbits the Earth, and the spin is imparted by photon spin. In the past, we've calculated our spin rates using the sun on the solar panels by measuring the voltages as they pass into sunlight and back into darkness in order to calculate the rotation rate of the satellite. The MEMS gyros is a new way, because of this new technology, relatively new, that we can look at another aspect of the spin, including, as I said, the wobble, and we'll compare the results of those methods to see how well they align. The second experiment is provided by the students at the Vanderbilt University, Institute for Space and Defense Electronics. They're taking up two boards, which are the red and yellow on that diagram. One slot is for their controller. The controller interfaces with the spacecraft bus and we'll take the signals for power and commands to operate the experiment and also pass the telemetry back to our IHU, which is our microcontroller that runs the satellite, to be passed to the ground in our downlink. The second slot is occupied by their experiment, which is a board that's going to record the occurrences of radiation-induced bit upsets in modern commercial off-the-shelf memory chips that exhibit a sensitivity to low-energy protons. The reason they do this is it will contribute to the validation of ground-based test methods for hardness assurance and error rate predictions. We're looking at what do commercial off-the-shelf components do in the radiation of space, because it can be very costly to use radiation-hardened components in building, especially a CubeSat. So this gives us a look at what we are able to fly in the future. Because of the open nature of our amateur radio operation, all of the satellite telemetry and experiment data has to be unencrypted and available to anyone. So anyone with the ground station software can receive that, as I mentioned, and be able to look at what the science has to say. This method of gathering data gives an ability to provide near real-time data, because as it's over any populated area, any ground station that is any amateur radio station throughout the world, that telemetry is gathered and sent to the server over the internet. So we do have basically worldwide coverage, with the exception of the oceans, in order to get our telemetry. So I would like to show a little video that's a time lapse of how we work with these satellites. This is done in my office at home. Because they're so small, they're very easy to ship around. Here I was working with the engineering unit and placing it into the space frame in order to put a solar panel on it to do a little testing with that. There are quite a bit more to them than may appear in the pictures. As you can kind of see, a lot of little screws especially. But that gives you an idea of how we are looking at putting these together and testing them. And with that, I will pass it to Courtney. Thank you.
Thanks, Jerry. I'm Courtney Duncan from NASA's Jet Propulsion Laboratory. And the point of LMRST SAT or LMRSat is to raise the technology readiness level of a radio science instrument. The idea of radio science is that while you might think of radio as being used to transfer information, such as an over-the-air television broadcast or from your cell phone, radio scientists actually measure the properties of the radio signals themselves, the extra delay as it goes through an atmosphere, or the change in frequency as a spacecraft flies by a planet due to its gravity. And so they're able to study gravity fields and media and other things like that with radio science. And we've had at JPL for many years, since the dawn of the space age, basically, we've had a strong radio science program, one component of which, for example, is we do what's called GPS radio occultation, where we measure the extra delay on GPS signals as they come down to Earth orbiting satellites, but being refracted and delayed through the atmosphere. With the constellation of these satellites, we can learn things about the climate, the weather worldwide. We can learn things about the Earth, but the Earth is only one example of a planet, and it would be nice to do this, we're JPL after all, it'd be nice to do this at other planets, and by learning about these same kind of effects at other planets, we learn not only about the other planets, but we have other examples that give us insights about the Earth. So, of course, all spacecraft take radios with them for telecommunication, for command and telemetry, and for navigation purposes. And so radio science has traditionally been done as a tag-along to that activity. You just use the radio that you're taking and do some measurements. But that subsystem being very critical to the spacecraft, radio scientists don't get as much time, as much data as they would like. And so they would like their own instrument, just like people have their own cameras and people have their own other kinds of sensors. They'd like their own radio science instrument that can go along on missions to investigate other planets and so forth. And so so we developed one that could be used for that. We repackaged it into a CubeSat form factor so that it can be flown in space, which is the technology raising activity that we're doing here. And once we've interacted with it in space and seen learn some things from that, then we'll be in a position to propose this credibly to future deep space missions to interesting destinations such as Europa, the moon of Jupiter, or Enceladus, the moon of Saturn, or Mars, or places that have gravity and atmospheres. We also partnered with Stanford University Space Systems Development Lab, where several students worked with us on this project. And it's been going on long enough now that some of those students actually work at JPL and in other aerospace places now. And also with Stanford, we partnered with Pumpkin Incorporated for the bus under both of those institutions under Dr. Andrew Kalman. So we're LMRST is thankful to the Alana program for hosting us here, to the NROL launch for taking us into space so that we can do this, and we're looking forward to an exciting and successful launch tomorrow, and to making this next step on in radio science investigations. So that's what I have for LMRST. Back down to you, Mike.
All right, thank you all. We're ready to take your questions now, so for those of you who are watching, if you are going to try to reach us online through social media, please make sure to use the hashtag AskNASA. Kimberly Williams from NASA's Ames Research Center Public Affairs Office is standing by, and she is perusing the questions inbound. And if you're on the telephone and you have a question, you need to push *1 to get into the question queue. So once we call your name or we call you out, please make sure to state your name, your affiliation, and to whom you're addressing your question so that we can get it to the right person. We'll also take one question, and if time permits, we'll go back for follow-ups. And we also remind you to please keep your questions to today's topic, the 5 NASA CubeSat missions that are launching tomorrow. So with that, why don't we start off with Kimberly and see what questions have come in to the hashtag AskNASA. Kimberly?
Our first question is for either Richard or Tim. For students, what are some basic requirements for CubeSats, and where could one learn those requirements?
I can take that on. The basic requirement for CubeSats is very similar to the requirements for larger satellites. You need all of the systems on CubeSats that you need on larger satellites. In a university environment where students are trying to build this, they have the option of designing and building the components themselves or buying commercially. There are companies that sell commercial products. But if the goal is to learn how to do it in a university environment, then they're well advised to take on as much as they can in the university environment to develop rather than buy, because that's how you learn the lessons that build the skills that you need in order to fly these satellites. I think that you have commented on that in your program, that some of your products were purchased and some developed, and I think that's really the way to go about that.
I'll stick with you on that. But can we ask what happens during the optical downlink session between the small satellite flying overhead and the ground station?
Okay, so the plan for that is that the satellite will fly over our optical ground station. We have a small telescope on Mount Wilson in Southern California that will receive the signal. The satellite will be within view of that station for about 3 minutes during a typical pass. And the planning for that pass starts about 24 hours before the pass happens. So we need to determine first exactly where the satellite is going to be at the time that it's passing over. For this kind of precision pointing, you need to know where you are. So the satellite has GPS receivers on board to allow us to calculate its orbit precisely. Then on the ground, we calculate pointing directions, pointing vectors for the laser beam as it's flying over the ground station. Pointing vectors in time, and then we upload that information to the satellite on the pass prior to passing over the optical ground station. So there is a RF command station in Texas that it will pass over before it passes over Mount Wilson. We'll provide the commanding information, and then as the satellite passes over the ground station, it will turn on the laser shortly before the pass begins, and then dump the data through the laser to the ground station over a period of about 90 seconds. and then that information will be collected at the telescope on the ground.
Kimberly, we'll take one more from you on social media, then we'll go to the telephone line, and then we'll come back. Go ahead.
Okay, for Morgan or Tim, can you talk about the excitement of students being involved with a CubeSat project now and what's coming into the fruition of projects like this?
So it's really exciting to be able to work on a CubeSat and just to know that this hardware I built is going to be going into space and be able to give us data, like take pictures of Alaska, get the launch environment data, see our attitude system work, and just everything working will just be a great achievement for everybody. And then where it goes for the future is, now that we've built the first satellite, we're already making plans for a second satellite, and we've been discussing what's going to be our next mission objective. And I already have like about 10, 15 students that are really excited to work on the next satellite now, and so we're just trying to take it from there, I guess.
Okay, remember, social media questions, use the hashtag AskNASA. If you're a reporter on the telephone bridge, please use *1 to get into the question queue, and we'll go there now for a question from Craig with America's Space. Craig?
Yes, hi, thank you. Can you hear me okay?
We hear you fine, thank you.
Okay. My question is about the deployments. Will you be using the same orbit as the NRO payloads? Or does the Centaur...
That's really a question that we can't really answer. That's not a question that we can really deal with regarding the NRO payload.
Okay. If there's any way you can answer it to characterize whether you're basically going to be the same.
Yeah, I think I would direct that question to the National Reconnaissance Office.
Okay, and one other in that vein. Once you start the deployments out of the carrier box, how long does it take to deploy all 13?
I can take that on. The satellites, the CubeSats are in boxes, closed, and they're off. They have a deployment switch so that when the CubeSat is ejected from the satellite, the switch opens and the satellite can turn on. And the time period for that is a matter of seconds. It takes less than a second for the door to open, and a spring pushes the satellite out, and depending on how the satellite's designed, it can turn on and begin functioning within seconds.
I'd like to add to that. For safeguards, to safeguard the primary mission especially, the satellites in this particular instance are not allowed to transmit for a period of 45 minutes after launch. After ejection, I'm sorry, thank you. After we're deployed, it's to ensure that it doesn't interfere at all with the primary mission.
Okay, we're back in the room, Kimberly, for social media questions.
This one's for you, Tim. Will there be any collaboration with radios and lasers?
AMSAT itself, we have not looked at any specific use of optics. That involves obviously a high amount of pointing. And so being this is our first CubeSat effort, we have several other ideas under consideration. But as the Radio Amateur Satellite Corporation, we're basically more oriented toward using the amateur radio that amateur radio operators throughout the world have access to. So as the technology develops, it's possible that we would use something like that. Right now we're focusing on basically RF so that people can talk to each other over the airwaves.
So I can also address that a little. At JPL, we're working on what was mentioned in the earlier panel, Deep Space Optical Comm, and the radio people and the optical people are now working closely together to develop systems that are both hybrid but pick the one that works best for your mission. And I have had conversations with some of those in early technology readiness levels about CubeSat type missions for them. So we're working on that. We're aware of this, the need to move forward in this way.
And is there a web location for tracking all of the new CubeSats? I guess that could go to any one of you.
In regard to our amateur radio satellites, all of the satellites that carry amateur radio, if you go to amsat.org, amsat.org, there are tracking tools there in order to know where they are. We also include the ISS and several other satellites. The amateur radio operators are very involved in a lot of aspects of space, and our Keplerian elements lists contain several orbiting things, not just the amateur radio satellites.
And this goes to the educator community here. Are students allowed to design a CubeSat that will expand once launched? Tim, Jerry, or Morgan?
Expand.
There have been past CubeSat designs that have deployable
Like the-
mechanisms
like the
deploying solar
deorbit
panels. Many of the CubeSats that have flown so far, and including ours that also deploys antennas. So in our case, our antennas are tied down with essentially fishing line that wraps around a resistor, and then when it's time to deploy the antennas, which for us will be 15 minutes after we deploy, the antennas are deployed by energizing those resistors, passing current through them, and that melts the monofilament line and the antennas extend.
I guess I can also add to that. So like our satellite uses our antenna. It's also considered a deployable, so it gets larger than the one-use structure. And then we actually did a concept study for another satellite done by a few of our students, where they looked at a satellite going to Europa, and they wanted to see if that could be a possibility with a CubeSat using a 3-use structure, and they had to. Because Europa is so far away, you need so much more solar power, so they had to find a way to expand their satellite into like 5 stages of like the Russian dolls or whatever, where there's one side or the other. And so they had this expansion process where they expanded out where it's like 5 times longer than it was initially. And then the other concept would be, can you fit a solar sail into a CubeSat, and that would be another deployable, which makes it much larger than original form factor.
And I can also speak a little bit to that. We had a student at MIT, Alessandro Babuscia, who designed an inflatable antenna. But one of the issues with CubeSats is they're so small it's hard to get a large enough antenna to do really good comm on them. So she designed this inflatable antenna as a student project, and now she's at JPL, where we're moving forward with this and other technologies like that to improve things on CubeSats.
And this last question could be answered by anyone, but I'll direct it at Richard. What inspired the mission design for OCSD?
The OCSD design was actually prepared in response to a solicitation from NASA aimed at specific technologies for CubeSats. If I remember right, they were looking for propulsion, for ways of reducing the size of ground stations for communicating with CubeSats, and for proximity operations. So we decided to design a satellite that would do all 3. And to us, the key to reducing the size of the ground station was to switch from RF to optical. So instead of having a dish on the ground that might range anywhere from several meters to several tens of meters, we're directing this beam into a telescope that's this big. So that's the size of the optical ground station. So that was the impetus for this mission.
Okay, I would like to thank everyone for coming today and remind you that the launch of the Atlas V is scheduled for 5:49 a.m. Pacific time tomorrow. NASA television coverage will begin at 5:19 a.m. Pacific, 8:19 a.m. Eastern Time. This press conference audio will be available in about an hour and will also be available for about 30 days thereafter for replay if you call 1-800-789-9018. And you can find out more about NASA's various CubeSat programs by going online to www.nasa.gov/CubeSats. Thank you again.